adding another property to data here, which is related to infinity. So the title of the video simply is Infinity and Upper Limit of Coefficient of Variation. So we add a new type of property to data, which is related to infinity. The main focus of this video is to analyze coefficient of variation of statistical data and its asymptotic behavior. Asymptotic behavior in this sense means if, for example, here a parameter of the data here approaches infinite, or maybe a number of parameters, but the main point in this video is just firstly here one parameter. In a simple way, if you have got, let us say, a raw data, because this idea here can be understood through a very simple data, and then if limit of an x here, or a value in x, approaches the infinite, then the coefficient of variation in which we will show it cannot exceed a certain upper limit. For simplicity here, properties and measures of data, this is something in which we have learned it from basics of statistics. For example, if you have good data, there is something here in which mean is a property, variance is a property, skewness is a property, even the nature of the distribution is property, correlation coefficient. There are too many other properties here in which we don't need to display all of them in this video. For example, here if you look at physical object has got shape, has got density, has got elasticity, has got atomic structure, ability to conduct electricity, semiconductor, and etc. For example, here normally in physics, what we have here, we make a comparison to two substances on the basis of density. We make a comparison of two material on the basis of elasticity. In statistics, we have got similar to those. For example, here, if I have got data, we can make a comparison on the basis of their means, or perhaps on the skewness of the distribution, and so on, even variance, even standard deviation. There are many different types of measures in which you can make a comparison between two data. For example, now if you look at it here, variation, the purpose here is why we need coefficient of variation. Coefficient of variation is different from standard deviation or even variance. If I have got two samples, and these two samples, they have got the same measure, like in kilogram, if I calculate the mean, then perhaps maybe the means are the same, then definitely we can't say the two data are the same. If we work out standard deviation, they have got two different standard deviation, but because the measures, the units are the same, then comparison on the base of standard deviation can be made on the variation of data. But sometimes what you have got a data in which the unit, the measurement is different from a different data. Like this data here is in kilogram and this data in centimeters. And then definitely here, if you make a comparison between the variance of this data according to the standard deviation, perhaps we may get a wrong conclusion, because this is kilogram, this is centimeter. And this is a reason in which normally in statistics we introduce coefficient of variation. Simply, coefficient of variation by definition is equal to standard deviation divided by the mean of the data. Now, there are some groups of data according to the value range of coefficient of variation. For example, the data having coefficient of variation less than 1, normally we name them by a Lang distribution. If, for example, the coefficient of variation is 1, these are exponential distribution. If coefficient of variation is greater than 1, these are hyper exponential distribution. But definitely here, none of these tells the upper limit. So here we will investigate this part. For simplicity here, if I assume raw data, so raw data certainly here, this is the definition of standard deviation and divided by the mean of the data. And the mean of the data here, for example, what we did, certainly where the standard deviation is a square root of that, and then we squared the mean and then we inserted it into the square root. And in this case here, this is easy. We multiply both numerator and denominator by m squared so that the form of both numerator and denominator takes a different shape. So now if we assume that one data here is approaching infinite, certainly if we take the infinity from the start here, you will get infinite or infinity minus infinity divided by infinity. And from basics of calculus, we have learned that this is not defined unless we take the limit in a sensible way. For instance, here now, if you divide, then you notice that if you take the limit, certainly the values are approaching 0 except n minus 1. Then it means for a normal raw data, the upper limit of coefficient of variation is n minus 1, the square root. So it means there is no way in which the coefficient of variation can exceed the data. The interesting point here is most of the other properties in which we have explained already, they depend on the data elements. If you look at variance, if you look at mean, and any others. But the interesting part of this conclusion here, the upper limit of this coefficient of variation here does not depend on the data element. It depends more or less on the size of the data. Demonstration, this is a simple numerical example here. If, for example, here you have got a set of data, and then this set of data assume that this is 50 elements, 50 points of data. Then according to this, whatever these elements of the data you have, there is no way in which the coefficient of variation exceeds 7. So it is always even less than 7, unless one data element approaches infinity. There is a special case, regardless of even approaching infinite, this is interesting, in which the coefficient of variation is exactly equal to the square root of n minus 1. For instance, here if I assume this data, that this data here is all the elements are 0 except 1, which is k, okay? So we will notice that here, not necessarily, in this case, this is a very special case, one data element approaches infinite. Then if you work out the standard deviation and the mean, and then you calculate it accordingly here, then exactly you will get, for example, 3. And then once you get 3, which is equal to 10 minus 1, the square root, which is 3. This is quite interesting. We have got a number of other cases to deepen a bit more, because the example in which I just gave were more or less like discrete elements, but the same concept can be extended to continuous distribution. The simplest continuous distribution usually is uniform distribution. In order to understand this concept, it may be a good idea if you introduce a parameter, which is a data element. It looks like a data element, which is b. And normal continuous distribution is usually between 2 points, alpha and beta, and this is the function, or this is the probability density function. If you calculate mu, the mean or standard deviation, you'll get those two numbers here. I'm not going to show those here through some basics of integration. then the coefficient of variation obviously is equal to the ratio between these two, which is equal to this. Then the parameter of my distribution in this case is beta, but if I approach beta to infinity here and then take the limit properly or using L'Hopital's rule, then this approaches 1 over root 3, in which it has got an upper limit. Another example, this example here is triangular distribution. The triangular distribution, again here I assign a parameter which is b, and this b simply here is the one in which later on we take the limit according to that one when b approaches infinite. Similar analysis here, mu and standard deviation can be calculated, and then the coefficient of variation, which is equal to this expression. But now the point is, if for example this parameter approaches infinite, then definitely this becomes 1 over root 2. What you can do here, all of those you can just calculate it by yourself to understand the concept of this approach or theory. There is another case here which is called general continuous distribution. This general continuous distribution, this is just a very basic thing in which I gave it here, but there is another video in which this is explained in more details. Simply here, for example, you have got any function which represents obviously the properties of the density function, and then certainly here, if one of the parameter here again here I can assume beta, then beta is an x point that approaches infinite. Then if this limit exists, definitely here you have got also the upper limit, but the analysis or full analysis of this will be on a different video. There is another interesting point which is still related to our discussion. Coefficient of variation normally is invariant, and the transformation in which is multiplying the data by a certain parameter or certain constant, okay, or certain value here, the coefficient of variation does not change. But if, however, we translate the data or maybe shift the data by a certain lambda, the coefficient of variation does not remain the same. So it means will be different. But there is an interesting point here. If, for example, the parameter of x, either here or here, approaches from the distribution to infinite, then these two will also become the same. Hoping you have enjoyed the video, and this is the end. See you in another video. Thanks for watching.